Alright guys, today let's talk about cosmic rays. Well, cosmic rays are very high energy particles, mainly originating from outside the solar system. They may produce showers of secondary particles that penetrate and impact the Earth's atmosphere and sometimes even reach the surface. They're composed primarily of high energy protons and atomic nuclei that are mysterious of our origin. Data from the Fermi Space Telescope have been interpreted as evidence that a significant fraction of primary cosmic rays originate from the supernovae of massive stars. However, this is not thought to be their only source. Active galactic nuclei probably also produce cosmic rays. The term ray is actually a historical accident, as cosmic rays were at first and strongly thought to be mostly electromagnetic radiation. In modern common usage, high-energy particles with intrinsic mass are known as cosmic rays, and photons, which are quanta of electromagnetic radiation, and are known by their common names such as gamma rays or X-rays, depending on what their frequency is. So, cosmic rays attract great interest, particularly due to the damage they inflict on microelectronics and life outside the protection of an atmosphere and the magnetic field. And scientifically, because the energies of the most energetic, ultra-high cosmic rays have been observed to approach almost 3 e to the 20 electron volts, which is about 40 million times the energy of particles accelerated by the Large Hadron Collider. At 50 joules, the highest energy, ultra-high energy cosmic rays have energies comparable to the kinetic energy of a 90 km per hour baseball. As a result of these discoveries, there's been a lot of interest in investigating cosmic rays of even higher energies. Most cosmic rays, however, do not have such extreme energies. The energy distribution of cosmic rays peaks at 0.3 giga electron volts, which is a crazy number. So now let's talk a little bit about the history of cosmic rays. After the discovery of radioactivity by Mr. Henri Becquerel in 1896, it was generally believed that the atmospheric electricity, ionization of the air, was caused only by radiation from radioactive elements in the ground or radioactive gases or isotopes of radon they produce. Measurements of ionization rates at increasing heights above the ground during the decade from 1900 to 1910 showed a decrease that could be explained as due to absorption of the ionization radiation by the intervening air. Okay, now let's talk a little bit about the cosmic ray energy distribution. Measurements of the energy and arrival directions of the ultra-high energy primary cosmic rays by the techniques of density sampling and fast timing of extensive air showers were first carried out in 1954 by members of the Rosy Cosmic Ray Group at MIT. Where else? The experiment employed 11 scintillation detectors arranged within a circle of 460 meters in diameter on the ground of Agassiz Station at the Harvard College Observatory. From that work, and from many other experiments carried out all over the world, the energy spectrum of the primary cosmic rays is now known to extend beyond 10 to the 20 electron volts. A huge air shower experiment called the Auger Project is currently operated at a site on the Pampas of Argentina by an international consortium of physicists led by James Cronin, who is the Nobel Prize winner in 1980 for physics. He went to University of Chicago. And Alan Watson, who went to the University of Leeds. So in November 2007, the Auger Project team announced some preliminary results. These showed that the direction of the origin of the 27 highest energy events were strongly correlated with the locations of active galactic nuclei, also known as AGNs. The results support the theory that at the center of each AGN is a large black hole exerting a magnetic field strong enough to accelerate a bare proton to energies of 10 to the 20 electron volts and higher. Now, let's talk about the types of cosmic rays. There are primary cosmic rays, which originate from outside the solar system and sometimes even the Milky Way. When they interact with the atmosphere, they are converted to secondary particles. The mass ratio of helium to hydrogen nuclei is 28%, which is similar to the primordial element abundance ratio of the elements, which is 24%. There are secondary cosmic rays, and when they enter the Earth's atmosphere, they collide with molecules, which are mainly oxygen and nitrogen. And that interaction produces a cascade of lighter particles, so-called air shower. All of the produced particles stay within about 1 degree of the primary particle's path. And alright, and last but not least, let's talk about some detection methods of the cosmic rays. So, the first detection method I would like to talk about is called the Air-Cherenkov telescope, which is designed to detect low energy, which is less than 200 giga-electron volts cosmic rays, by means of analyzing their Cherenkov radiation, which for cosmic rays are gamma rays emitted as they travel faster than the speed of light, which is 3 to the 8th meters per second, in their medium, the atmosphere. There's also the EAS, extensive air shower arrays, which is the second method I'd like to talk about, and they measure the charged particles which pass through them. EAS arrays measure much higher energy cosmic rays than the Air-Cherenkov telescopes do, and they can also observe broader areas of the sky and can be active about 90% of the time. However, they are less able to segregate background effects from cosmic rays than the Air-Cherenkov telescopes. EAS arrays employ plastic scintillators in order to detect particles as well. And so that's it pretty much. That's all I know about cosmic rays. That's what I got out of the lecture. So thank you very much, and hope to do well.